Right, we're going to be solving the fall 2023 final exam for ECE 2K1. Starting off with the first problem, we can see it is asking us what the equivalent capacitance seen by a source connected to terminals AB in the circuit below would be. An equivalent capacitance basically means what would the capacitance be if instead of having this big circuit here with 5 different capacitors, what would the equivalent capacitance be if we could just connect one capacitor in between these two nodes? What would give us the same value? When you're given problems like this on the exam, these formulas over here that I've attached are going to be really useful to you. I'd recommend writing these down on an equation sheet if you have one. So we've got formulas for resistance, inductance, and capacitance, but because this circuit specifically only deals with capacitors, we're just going to be using these formulas down here. And let me correct the bottom formula. It should not be R1 plus R2 plus whatever. This should be C1 plus C2 plus C3 because we are adding the capacitances together, not the resistances. So jumping back to the circuit over here, first thing we're going to notice is that on the right-hand side right here, we have this capacitor here, but we also have a wire that is directly connecting this node to this node. This is significant because the capacitor is also connecting those two nodes. But when the current is traveling through the circuit, the current is going to reach this node right here, and it's going to want to take the path of least resistance. And because a capacitor introduces a little bit of resistance into the circuit, that means that the current isn't going to want to go this way down where the capacitor is. It's going to want to go straight here because that's the path of least resistance. And this actually means that we can neglect this capacitor over here completely when we are solving this problem. It basically doesn't factor into our calculations at all. That means that left over, we just have these 3 capacitors, which are in parallel, and this one capacitor, which is in series with the other 3. We know that because all of these 3 capacitors are connected at this one node here, and then connected again at this node here. This capacitor takes that path if the current is going through there. The current takes this path if it's going through the second capacitor, and takes this path if it's going through the last capacitor, but they all end up at the same place. That means they're in parallel, not in series. And we can kind of redraw the circuit to make this even more clear to us. So if we have our circuit in between A and B, we're going to have one capacitor right there, and then our other 3 capacitors are going to be here in parallel with each other. This capacitor is 5 farads, this one is 3, this one is 2, and this is another 5 farad capacitor. Now when we want to add up the capacitances of these 3, which are in parallel, we can look right over here where our parallel equation is, and we can see that the parallel equivalent capacitance is going to be equal to C1 plus C2 plus C3 plus however many more capacitances you have. We can write this. The equivalent capacitance is going to be equal to 3, which is C1 in this equation, plus 2, which is C2, plus 5, which is C3. If you add those all together, you're going to get an equivalent capacitance of 10 farads. Now we can redraw our circuit to more accurately show what our equivalent capacitances are. We've got one 5 farad capacitor up here, and we've got one 10 farad capacitor down here. Now these 2 capacitors, the 5 farad and the 10 farad, are not in parallel, they are in series with each other, which means that we have to use this equation up here, the capacitance in series equation, and that's going to give us that the equivalent capacitance, 1 over the equivalent capacitance is going to be 1 over C1, which in this case is 5, plus 1 over C2, in this case 10. If you add those 2 together, you're going to get 3 over 10. But remember, we still have to flip this fraction because our equivalent capacitance is on the bottom of the fraction on the other side of the equal sign over here. So if we flip this so that the equivalent capacitance is on the top, we're going to have 10 over 3 farads is our final equivalent capacitance for this problem. Headed back up to the top, we can see this matches answer B. So answer B is going to be the correct answer for this problem. Moving on to question 2, this one asks us to determine the inductor current IL at time equals infinity. This is going to be our most important piece of information in this problem. We know that we're looking at the circuit after a very long amount of time has passed. So there are a couple of rules that we can use to make the circuit a little bit more simpler for us. Just a little bit simpler for us. We know that based on these rules, if time is equal to 0, then a capacitor is going to behave like a short circuit. If time is equal to 0, then an inductor is going to behave like an open circuit. We also know that at time equals infinity, let's make this into a little table here, a capacitor is going to behave like an open circuit. It's going to be a reverse, basically. Capacitor behaves like an open circuit, and an inductor behaves just like a closed circuit. That means looking at this problem, since we're dealing with time is equal to infinity, and we have an inductor right here, at time equals infinity, our inductor is going to behave like a closed circuit, or a short circuit, rather, which means that we can essentially treat this like a normal wire, and we can neglect the inductance. It's not going to factor into our final calculations at all. Looking back at our circuit now, we see that we've got a short circuit right here, which is going to be cutting out this resistor, and that can actually be neglected as well. We can cross it out right there. That makes our our circuit a lot more simple, because now we just have 2 resistors that we have to deal with. So one more thing we can see while looking at the circuit is that we have a step function right here, which gives us the voltage. The way a step function works is it tells us when the voltage source turns on. So before, in this case, it's going to be turning on it at time equals 2, because we have the -2 right here, and the step function always takes the form ut minus the time that it turns on. We'll say that's A. So we know that A equals 2, which means that at 2 seconds, that's when the voltage source turns on. So before 2 seconds, the voltage in this is going to be equal to 0, and this is going to behave like a short circuit. That after 2 seconds, we're going to have 12 volts, because 12 is the number we have at the beginning of this expression here. So that means for t is greater than 2, the voltage is equal to 12 volts. And that includes when t is equal to infinity, because infinity is greater than 2. All right, last thing we've got to do is find the equivalent resistance of these 2 resistors. Because they are in series with each other, we can remember that resistors in series are just added together, so our equivalent resistance is going to be equal to 8 ohms, because 8 ohms is 4 plus 4. Based on that, we can now use Ohm's law to solve for the inductance in the circuit. The inductance when t is equal to infinity is going to be equal to the voltage at t equals infinity divided by the resistance at the same time. Because we've already solved for that, V is equal to 12 and R is equal to 8, that means that the final inductance that we're going to get is going to be equal to 1.5 amps. We look up at the top here, we see that this matches answer number G. So G is going to be the correct answer for this problem.
Question number 3 asks, for what angular frequency omega is the input impedance purely resistive or real? Only consider positive frequencies. So the equation that we want to remember for this type of problem is going to be omega is equal to 1 over the square root of L times C. And this equation is going to apply anytime we have a circuit, an RLC circuit that looks like this, but it's also going to apply anytime we have a circuit that looks something like this. So if all of these components are in series with each other rather than in parallel, this equation up here is still going to apply. And we can use this equation when we want our input impedance to be purely real, because this frequency right here is going to make it so that these two components over here, whenever you solve for the input impedance, it's going to make these two components kind of cancel out their imaginary parts because of the resonance that this equation introduces into the circuit. And when that happens, the only thing we're going to be able to consider is the real resistance over here, which is 6 ohms. And so that's going to be the only part really that has an influence on our input impedance. So if we want to solve this equation, what we have to do is just plug in the values that were given in the circuit. That would be 3 henries and 1/6 farads, which becomes square root of 1/2. And that is essentially going to be square root of 2, which means our answer here is E. Question number 4 is asking, what is the RMS voltage for the waveform below? In order to solve this problem, we first need to figure out what is the period over which we want to solve this problem. And to do that, we need to know what's the period before this function repeats. What is the period on which this function is unique? By observing the graph, we can see that the function is unique from 0 to 2. After t equals 2, the function is going to repeat itself. So we are looking for 0 is less than t is less than 2. That's the interval over which we're going to be observing this function. This means that our period, the length is going to be equal to 2, because 2 minus 0 is 2. Then the equation for the function that we're going to be using, we can observe from the graph that there are 2 different equations we're going to need. One is going to be from 0 to 1, and one is going to be from 1 to 2, because the behavior of the waveform is different on those 2 intervals. So from 0 to 1, our waveform is going to be equal to 4t. From 1 to 2, our waveform is going to be equal to negative 4t. So in order to solve for the RMS voltage, we have this equation up here. The equation is going to be identical if you are asked to find the RMS current. It's just you would have to replace this V value with IRMS, and this V value over here with the function of current, instead of the function of voltage. So now that we have this equation here and we know our t value, the last thing we have to do before we can plug this into the equation is figure out what the v squared of t value is going to be equal to. From the interval of 0 to 1, we know that our v squared t value is going to be equal to 4t squared, which is equal to 16t squared. From 1 to 2, our v squared t value is going to be equal to negative 4t, all of that to the power of 2, which is also going to be equal to 16t squared. It's very important to notice that this value and this value for the 2 parts of the waveform actually end up being the exact same, because it allows us to simplify this equation when we're solving it. All right, so now that we have these values, let's plug them into our equation. VRMS is going to be equal to the square root of 1 over t t in this case is 2, as we determined before. And then we are going to multiply this by our integral. Because we have two different pieces of our waveform, we're going to have to use two intervals to cover the full range of the function. So from 0 to 1, we have v squared from 0 to 1, which we've already determined to be 16t. So from 0 to 1, 16t squared. The integral of that plus from 1 to 2, we're going to put in the v squared value that we found over there, which is also going to be equal to 16t squared. And all of this is under our square root. Now, if we look at this portion of our integral and this portion of the integral, they both have 16t in the center, and then they are both on a range with a length of 1, because from 0 to 1, that's 1, and from 1 to 2, that's also 1. So we can actually rewrite this to make it square root of 1/2 times 2 times the integral from 0 to 1 dt. Because the behavior of the function, of the squared function, is going to be the same, we can just multiply it by 2. And now we notice that this 1/2 value and this 2 value over here cancel each other out. And now the only thing that we have inside of our square root is our integral. So solving the integral real quick, we have t squared here. That is going to turn into, the 16 comes outside of the integral because you don't integrate constants. So 16 times t cubed over 3. And this is on an interval from 0 to 1. If we put t inside of that interval, we're going to have 16 times 1 over 3, because 1 minus 0 is equal to 1 inside of our t cubed value. That means our final answer is going to be 16 over 3 inside of our square root, which you can also write as 4 over the square root of 3. Looking back up at our answer choices, we can see that this answer matches C right here, so that's going to be the correct answer for this problem. Problem number 5 asks us to determine the average power delivered to the load. The equation that we want to use for this is going to be the average power is equal to the voltage times the current. Because this is in the phasor domain, which we can see from the I value and the impedance value over here, we're going to have both a real and an imaginary part of this equation. But what we want to find for the power is we only want to look at the real part. So we can modify our equation to say the real part of V times I in the phasor domain. We're given I of S over here, which is going to be used for our I value, but we aren't given our voltage value. However, we can find this pretty easily using Ohm's law. So V is going to be equal to I times Z, where Z is the impedance. And we're going to find that this is equal to J2 multiplied by 1 plus J. That's going to give us a V value of J2 minus, not minus 4, minus 2. And this is going to become negative because these two J values are going to multiply with each other and be equal to negative 1, because J times J is negative 1. Okay, now that we have our V value and our I value, we can put this into our power equation. P average is equal to the real part of J2 minus 2 multiplied by J2. This becomes J2 squared minus J4. And we know that this is equal to -4 minus J4. Now, if we only take the real part of that equation, we're also going to want to do an absolute value of this. If we only take the real part of that equation, we are going to neglect this J term over here, and we find that the value is going to be 4 watts. Looking back at our answer choices over here, this matches answer B. Question number 6 asks, what is the time constant tau for the inductor circuit? In order to solve this problem, we need to remember our time constant equations. For an RC circuit, this is tau is equal to R times C. For an LC circuit, for an LR circuit, this is going to be equal to tau is equal to L divided by R. So because we're dealing with an inductor circuit right now, we're going to use the equation for an LC circuit, and we're going to have tau is equal to L divided by R. In order to figure out what our L and R values are going to be for this problem, we need to find out what the equivalent resistance is, and in order to do that, we are going to turn our voltage source off. If the voltage source is turned off, it's going to become a short circuit. If this was a current source, it would become an open circuit, but since it's a voltage source, it's going to be a closed circuit, and that means we are going to have to find the equivalent resistance with our 10 ohm resistor and our 50 ohm resistor. These two resistors are in parallel, which means that we can use parallel resistor addition in order to find the equivalent resistance, and the equation for that is 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus however many resistors you have in parallel with each other. Because we only have 2 in parallel, our equivalent resistance, 1 over our equivalent resistance is going to be equal to 1 over 10 plus 1 over 50. If you solve this equation, you're going to get the equivalent resistance is equal to 25 divided by 3 ohms. And this is going to be our R value for this equation, and we're already given our L value over here in millihenries. Because we only have one inductor, we don't have to do any inductor addition in order to find our L value. That means we can just take this tau equation, and we are going to have 25 millihenries divided by 25 over 3 ohms. Now remember to convert millihenries to henries, because you would get the wrong answer if you didn't do that. So you're going to have 0.025 henries divided by, multiplied by, let's just get rid of the units, times 3. We're going to have that all over 25. If you do the math, you're going to get that the time constant is equal to 0.003 seconds, or you can also write this as 3 milliseconds. If we go back up to our problem, we see that this answer is going to match number C. Question number 7 asks, what is the total current through the inductor in the circuit below? This circuit is a bit complicated because, as we see, we have 3 different sources here. 2 of them are voltage sources and 1 is a current source. Now we could try to use some of the methods that we already know, like mesh analysis or Kirchhoff's laws, but that would take a lot of time and be a lot of equations. So what's easier for this problem is to use superposition. And that is when we turn off all of our voltage sources except for one, solve for the current in that circuit and then do the same for each of the voltage sources or current sources. And at the very end, we add them all together to find the final impact on what this current would be here. So starting off with our first source, we're going to use S1 over here, which means we will be turning off these two sources here. If we do that, we can redraw our circuit to look something like this. This is our voltage source, which we know is equal to 2. Our resistor is 4 ohms, of course. Another 4 ohm resistor here. And remember, when we are turning off voltage sources, they become short circuits. And when we are turning off current sources, they become open circuits. So this middle branch here, when we turn our current source off, is just going to completely be neglected because it's an open circuit and no current is going through it. Which means that the next component of our circuit is going to be our inductor over here. With J4 ohms. This is our redrawn circuit number 1. So in order to solve for the current going into the inductor right here, IL, we're going to first find the equivalent impedance. So I have the impedance equations written up here. When the loads are in parallel, we're going to use this top equation, and when they're in series, we're going to use this bottom equation to find the equivalent impedance. In this case, the loads are all in series with each other, so we're going to use the bottom equation. So the equivalent impedance is going to be equal to 4 ohms plus 4 ohms plus J4 ohms, which in total is going to be 8 plus J4. Now that's just the impedance. In order to find the current, we just use Ohm's law. We know that I tilde L, that is going to be equal to V tilde divided by, of the force source, divided by our equivalent impedance. And we know that this is equal to 2. So we're going to have 2 divided by 8 plus J4. And that is going to be our current based on source number 1, is that fraction right there. Now moving on to source number 2. We see up here, that's the source up here that's equal to 6 volts. So we can redraw that circuit once again. Oops. Redraw that circuit one. That's quite annoying. We can redraw the circuit like this. 4 ohm resistor here. 4 ohms here. Oops, I forgot. We actually have the source first, and then the 4 ohm resistor. And the source is 6. And this is our redrawn circuit. Now this, we're going to use basically the same method we did for the last circuit, where we find the equivalent impedance. That's going to be equal to 4 ohms plus, this is J4 right here, ohms. J4 ohms plus 4 ohms, because once again, these 3 are all in series. So when we add them up, we're going to get the exact same impedance as in the previous equation, 8 plus J4. But when we use Ohm's law to find the current based on the second source, because our voltage here is different, we're going to do 6 divided by 8 plus J4, which is a slightly different answer than up there. All right. So our third and final source, we're going to see the impact that this has on our circuit. If we turn off both of these voltage sources, they're both going to turn into short circuits, and we are keeping this on. So In this case, with the current source on, we're still going to have 2 loops, 1 and 2, even though in the previous circuits we only had 1 loop because of the current source being turned off. In this situation, the current source is not turned off, so we're going to have 2 loops. Four ohm resistor, another 4 ohm resistor, the current source right here, which is equal to, let's see, 4 amps. And the inductor here, J4 ohms. Alrighty, so in order to solve this one, it's slightly more complicated, but still not too complex if we remember Kirchhoff's laws. So what we're gonna do, first of all, is we know that this right here, this right here is going to be one of our nodes, and the voltage drop across all 3 branches coming out of this node, here, here, and here. The voltage drop across those 3 channels, those 3 branches, I mean, it's always going to be equal. So from here to here, from here to here, and there to there, the voltage drop is always going to be equal. We can use that to get an expression relating the current coming out here to the current that is coming out here. And I'm going to call the current coming out of this side, I'm going to call it I0. So if the voltage drop can be found using Ohm's law, we know that the resistance here is going to be 4 plus 4, which is 8. 8 times the current, which is I0. And since the voltage drop across this branch is going to be equal to the voltage drop across that branch, we can also say that the impedance here, J4, times IL, which is going into the resistor here, is going to be equal. So now we have this equation right here relating those 2 terms. Since we have 1 equation and 2 unknowns, we need 1 more equation before we can really relate these 2 terms. But we can find that using using the current as well. So because we know that the current coming into this junction here has to be equal to the current coming out in these 2 directions, we can write that the current from source 3 must be equal to I0 plus, let's write it tilde there, the current going into the inductor, and the current coming from source 1 is given to us as 4. Now that we have 2 equations and 2 unknowns, we can solve. Let's do this. Say I0 is equal to 4 minus IL. Plugging this back in using our equation from above, we will get this equation. And solving for the current here should be pretty easy. The final answer that you should get if you do this should be 32 divided by 8 plus J4. All right, now that we have our 3 different answers, number 1 up here, 2, and 3, what we just need to do to find the current of all 3 of them combined is to add them all together. So let's see. IL is equal to 2 over 8 plus J4 plus 6 over 8 plus J4 plus 32 over 8 plus j4. We can simplify this fraction to be 40 over 8 plus j4, which is also equal to 20 over 4 plus, oops, we can simplify it even more than that. It can be equal to 10 over 2 plus j. So this is the answer that we've got right here, that in amps. But if you look over at the answer choices written here, it doesn't really seem like any of those match. But if we just rewrite this fraction in a different way, we're going to end up seeing that this answer actually is one that we are given with our answer choices. So what we have to do in order to find the correct answer in the form that the problem wants us to put it in, we just have to multiply this fraction by the reciprocal of the denominator. Now, the reciprocal, since the bottom is 2 plus j, the reciprocal of 2 plus j is going to be 2 minus j. And we multiply both the top and the bottom. Since the top and the bottom are equal to each other, this is basically the same as multiplying it by 1, so it doesn't change the value of the answer at all, it just changes the form of the answer. And if we do that, we're going to end up getting the answer as 4 minus 2j amps. And with that final answer, we can look at the problem. The answer is given over here, and we can see that matches up with answer F right here. So answer F is going to be our correct answer for problem number 7. All right, question number 8 asks us, what resistor and capacitor combination maximizes average power transfer to the load? In this circuit, we know that this is the load, which means that when we're considering the source, we're gonna include all of this right here in the source, okay? So this right here is the equation for maximum power transfer in between a load and a source, where the impedance of the load is equal to the reciprocal of the impedance of the source. So in order to know what these two values are, we need to remember this equation. Impedance is equal to resistance plus J times the reactance. And the reactance is either going to be equal to omega L, or it's going to be equal to 1 over omega C, depending on if you're trying to find the reactance of an inductor or a capacitor. Right, so if we're looking at this circuit here specifically, we know that the impedance of the source, which is going to be written as ZS, that's going to be equal to the resistance of the source plus J times the reactance of the source. We also know that the impedance of the load is going to be equal to the reactance of the load plus J times the, this is the resistance of the load times J times plus J times the reactance of the load. So if we want to find the reciprocal of the source, a reciprocal is going to be the exact same, but instead of an addition sign right here, we're going to have a negative sign. So this is equal to the resistance minus the reactance multiplied by J. All right, and since we know that this value and this value here are equal to each other from the equation up above, we know that the resistance of the source minus J times the reactance of the source is going to be equal to the resistance of the load plus J times the reactance of the load. And we know that in this equation, these two, on each side of this equation, these two terms are going to be real, and then these two are going to be imaginary. And to help us solve this equation, we can set the real terms equal to each other and the imaginary terms equal to each other. So we will end up having something that looks like this, where the resistances are equal to each other, and then the reactance of the load is going to be equal to the negative reactance of the source. All right, we're given the resistance of the load, that's right here in the circuit. So we know that both of these are going to be equal to 10 ohms. And then here, in order to find the reactance of the load, we need to use our reactance equations. We know that because the source contains an inductor, we're going to be using our inductor equation. So negative omega times L, which in this case is 80 millihenries, yes, and then we're also given the right here we're given omega is equal to 100 from that. So negative 100 times 0.08. If you do that math, you're going to get negative 8. So the reactance of the load is equal to negative 8. If you write that all out, oh, one more step, we got to find the capacitance. So the capacitance, we can find that from the reactance using this capacitance equation right here for reactance of a circuit with a capacitor. So that's going to be 1 over omega C, which is equal to 1 over 100 times C, and all of that is going to be equal to negative 8 because we're finding the capacitance of the load here. We already know that the reactance of the load is negative 8. If we solve that problem for CL, we're going to get our answer is CL is equal to 0.00125 farads, which we can also write as 1.25 millifarads. So since we know that the capacitance is 1.25 millifarads, and we know that the resistance is 10 ohms, we can look back up here, and it looks like answer E is going to be correct because that matches our capacitance and resistance values. Question number 9 asks us to determine the Thevenin equivalent for the circuit below. So right now the circuit is in Norton form, which of course looks like this, where the current and the resistor are in series with each other, or sorry, in parallel with each other. And in order to turn it into a Thevenin equivalent, we want them to be in series with each other. And we want this source to be a voltage source. And even though this is in the phasor domain, as we can see from the values up here, even though it's in the phasor domain, this is going to behave pretty similarly to converting between Thevenin and Norton circuits in the time domain. So the first thing we want to do is we want to find the voltage of our new circuit right here. What is this voltage source going to be? And thankfully we already are given a current and a resistance right here. So in order to find the voltage, all we have to do is use Ohm's law, V equals IR, where I is equal to 2 and R is equal to 20 because we're given those values up here in the circuit, which means that our voltage is going to be 40 volts. Now we can find, we can redraw the circuit to be in Thevenin form, except this is actually a sine, of course, so it'll look something like this. The resistance is going to stay the same, but we see that it's now in series with this inductor right here. So we've got 20 ohm resistor in series with J times 40 ohms. So this isn't the final form that our circuit should be in. We have to do a little bit of impedance addition to simplify these two components into just one component. But luckily that's pretty easy because they are in series with each other. So we're just going to use this equation right here. The equivalent impedance is equal to Z1 plus Z2, which is just going to be 20 ohms plus J40 ohms. All right, so the equivalent impedance is 20 plus J40 ohms. Given this right here, and our voltage, which we already found, we can now know that the correct answer for this problem is going to be A, right there. Yep. Question number 10 asks us, which is the correct matrix equation to solve for the currents I tilde 1 and I tilde 2 at angular frequency omega? So what we want to notice about this circuit, there are two inductors right here that have mutual inductance and are dependent on each other. And we know this because of these dots here and the fact that these two inductors are right next to each other. These dots indicate mutual inductance, and we can see that they're on opposite sides of the inductor. This might be a tricky concept for some people, but it's actually pretty simple once you know how to redraw the circuit because you can use laws and theorems that you've already learned, all right? So remembering that this inductor L1 has the dot at the bottom, this has it at the top, we can redraw it, redraw these two circuits to look something like this. This is R1 right here. This is, I believe, a voltage source with V tilde S. This is our first, let me leave a little bit more space here. Our first inductor goes right here, that's L1. And then we're also going to draw a dependent voltage source right here. And remember, because the dot was on the bottom, that means this dependent voltage source is going to look like this with the plus sign on the bottom, indicating the direction of the voltage source. And the equation for the voltage that is coming out of the source is going to be J omega L12 multiplied by the current of the other circuit. So this is a dependent voltage source, and it's dependent on the current in the other circuit over here, not on the current in this circuit. And it's also dependent on the inductance right there, L12. All right, now we can connect the circuit back like this and move on to the second part of our circuit, which looks something like this, with our second inductor L2 right there and our second voltage source, which is going to be, because in this instance the dot is on the top, it's going to be going in the opposite direction, and we're going to have negative J omega L12 I tilde 1. This source is dependent on the current from the first circuit loop. Just like the first circuit, this circuit was dependent on the current from this loop. This circuit is now, with the voltage source, is dependent on the current from this loop. All right, now that we've rewritten these circuits, all that's left is to solve. That's for R2, of course. So based on the primary side number 1 over here, we're going to have, we're going to use mesh analysis. So V tilde S plus I tilde 1 multiplied by R1, which is going to give us the voltage drop across this resistor right here, plus I tilde 1 multiplied by J omega L1 and that's going to give us the voltage drop across here minus the value of the voltage right here. Because this is a voltage source, we don't have to multiply anything, we can just write it straight out. I'm just going to move the current to be at the beginning for consistency. So I tilde 2 J omega L1 2. And we know that all of that is going to be equal to 0. We can rewrite this as V tilde S is equal to I tilde 1 multiplied by this whole value plus I tilde 2 multiplied by negative J omega L 1 2. And the reason why we wrote it in this form is going to be obvious once we've written the second equation as well. So moving on to circuit number 2, the equation that we're going to find here is going to be mesh analysis. Once again, we're going to start with, let's see, negative I tilde 1 J omega L1 2, which is just the voltage change right over here. We're going to have that plus I tilde 2 J omega L2 plus I tilde 2 R2. That's going to be the voltage drop across here and the voltage drop across there, the resistor. And that is going to be equal to 0 because the current, the sum of the voltages must always be equal to 0. Rewriting this, we've got 0 equals I tilde 1 times negative J omega L1 2 plus I tilde 2 R2 plus J omega L2. Now that we have these two equations, number 1 and number 2 right here, we can put this into matrix form, which is how the answers for this problem are all set up. They're all in matrix form. So to put it in matrix form, we just put the voltages right here on this side of the equation, Vs and 0, because we've got Vs for the first equation and 0 for the second equation. Those are equal to, they are going to be equal to these terms in the equation. So let me just write that out. L1 and then J omega L1 2 negative J omega L1 2 and R2 plus J omega L2. This whole matrix right here is going to be multiplied by the current matrix, which is just simply I1 tilde over I2 tilde. And you'll notice that if you use matrix equation to multiply out these terms right here, you're going to get the exact same equations that you had up here. So we didn't really change these equations at all. We just wrote them in a different form. All right. And then looking at this matrix up here, we can see that it perfectly matches C right here, this matrix. Question number 11 says that the intrinsic carrier concentration in silicon at T equals 330 Kelvin is 1 times 10 to the power of 11 centimeters to the negative 3. If the silicon is doped with 5 times 10 to the 16 centimeters to the negative 3 phosphorus atoms, which of the statements below regarding the material type and minority carriers is correct? You may find the partial periodic table below useful. All right, so in this question, you are given the periodic table over here, but you are not given any of this information over here. I would highly recommend you write down everything over here on the right side of the page for questions like this, including these definitions of what these variables mean in all of these equations in the table and this equation right here, just because it can be a little bit tricky sometimes to keep track of, and they're not going to tell you what the numbers are in terms of their variable names in the problem. But essentially this over here is all of the information we're going to need to solve this problem, those formulas as well as the definitions of what those variables are. So the most important equation for us for this problem is going to be this right here, NP equals Ni squared, where Ni is the intrinsic carrier density, N is the concentration of electrons, and P is the concentration of holes. In the problem statement, we can see that we are told the intrinsic carrier concentration, and we are told that it's that number right there. So Ni equals 1 times 10, 11 centimeters negative cubed. And the silicone is going to be doped with this number of phosphorus atoms. We need to determine whether phosphorus is going to be N-type or if it's going to be P-type. And the best way to determine this is, again, we look at our table up here. We know that group 3 gives us acceptors and group 5 gives us donors. And these groups correspond to group 3 and group 5 on the periodic table here. Because phosphorus is in group 5, that means phosphorus is a donor. And so we're going to be using the values on this side of the table to apply to phosphorus because of its donor, because it is a donor. So now that we know what phosphorus is, we know Ni, we know that this number that we underlined earlier up here, that number is going to be N. N equals 5 times 10 to the 16 centimeters negative cubed. And we know that because of its status as a donor, if we were talking about a material that was an acceptor, we would say that P is equal to this number. But because we're talking about a donor, we're talking about the N-type, which is the negative type, because, of course, this material is donating electrons which have a negative charge. All right, now that we have those two values, we can put them into our equation that we have, NP equals Ni squared. And this is going to be equal to 5 times 10 to the 16 times P equals 1 times 10 to the 11 squared. We also can say from the information in this table here, we know that P is roughly equal to Ni over Nd, Ni squared over Nd, and N is roughly equal to Nd. And these equations, of course, are just going to correspond with this right here, because you can see if you plug in N right here, and then you multiply N over here and cross that out on the bottom, you're going to get the exact same equation that you have right here. So you could also solve it that way if you want. So solving this equation that we wrote down earlier and simplifying it, we're going to get P is equal to 2 times 10 to the 5 centimeters, like that. And this is going to be the answer that we get right here. So looking back at our problems up above, we can see in E, it says that the material is N-type, which we know that phosphorus is N-type, so that's correct. And then the minority carrier hole density is 2 times 10 to the 5 centimeters negative cubed, so E is going to be our correct answer. Question number 12 says, the charge density for a PN junction is shown below. The P-side depletion width is 30 times 10 to the negative 9 meters, and the N-side depletion width is 300 times 10 to the negative 9 meters. If the P-side acceptor doping density is Na is equal to 10 times 10 to the power of 16 centimeters to the power of negative 3, what is the N-side donor doping density Nd? So for this problem, we have a relatively simple equation over here in the corner that you should write down, which will help us solve. And we're given all of the information to satisfy this equation in the problem statement. We're told that the P-side depletion width, which is XP, is going to be equal to 30 times 10 to the negative 9. And the N-side depletion width is going to be 300 times 10 to the negative 9. And if I could write that in there, that would be Xn. Because X is the width in this situation. So if we're plugging that into our formula that we have up here, you're going to write 300 times 10 to the negative 9 multiplied by Nd equals 10 times, that's Na technically, but it's okay. It doesn't really matter if we write them out of order. And then 30 times 10 to the negative 9. And then solving for Nd should be relatively simple. You're going to get Nd is equal to 1 times 10 to the power of 16. And if we look at our original problem over here, we can see that lines up with answer B right here. So B is going to be the correct answer for number 12. Question number 13 says, consider the ideal diode circuit shown below. Which graph shows the correct current IL through the load resistor? All right, so what we know about diodes is that they only flow in one direction. So the way there's going to be two states for this circuit. There's going to be the diode on state and the diode off state. When the diode is on, that means that the current is going to be flowing in the same direction as this diode. And it means that the diode isn't going to be, it's going to essentially behave like an open wire. If the diode is off, it is going to be, the current is going to be flowing in the opposite direction of this diode. But if there's current flowing in the opposite direction, then the diode behaves like an open wire. It's not going to let any current through, which essentially means that the diode is going to behave like an open circuit at that point. So knowing these rules about diodes, we can now redraw our circuit to show the two states of how the circuit could look while the current is flowing. The top one is our diode on circuit, and this bottom one is going to be our diode off circuit. Notice how with the diode off, we have this open circuit in the middle here where the diode would be, and with the diode on, it's essentially a wire. We can also see in the diode on circuit that this resistor right here is going to be short-circuited by the diode, the wire that came from the diode. So essentially in the diode on circuit, we can completely neglect this resistor. There's not going to be any current flowing through here, which means IL at this point is going to be equal to 0. When the diode is on, there is no current, and IL is 0. So then in this circuit, all of the current is going to be flowing through the resistor because obviously it can't flow through the open circuit here, which means that IL is going to be equal to the input voltage divided by resistance according to Ohm's law. Now we have to figure out over time, which is what our graph is showing us, over time, how is the diode going to behave? When is the diode going to be on and when is the diode going to be off? Because when we figure that out, it's going to tell us how this current is going to behave over time, and that's when we can decide which one of these graphs is going to fit with the behavior of the circuit over time. And of course, the circuit is changing over time according to the sine function that we're given over here for the voltage. The best way to determine how the circuit, let me back up a little bit. We have to determine, based on the behavior of the voltage, how is the diode going to behave. Looking at our diode on circuit, this is where we're going to be determining how the current is flowing based on the voltage here. So when the voltage is positive, the current is going to be flowing like this, and then going like this all the way through this loop here, because remember, this resistor is short-circuited, right? So when the voltage is positive, then that's when we're going to have this diode on. The diode is going to be on. So V is positive. When the voltage is negative, essentially this has become switched like that. We're going to see that the current will be flowing in like this and then like this, which is of course opposing the direction of the diode, because the diode originally be like this. If the current was flowing like that, that's the opposite direction. That's what's going to turn the diode off. So we know that V has to be negative when the diode is off. In order to determine when V is positive and when V is negative, I would recommend sort of creating a table like this, unless you're super familiar with how sine functions behave, in which case you probably don't have to, but this will probably make it easier for a lot of people. So this table is going to tell us what the time value input is, what the voltage based on that time would be, and whether the voltage is positive or negative. And we can just try a bunch of different time values in order to figure out what the behavior at these spots would be. So looking at the graphs, a lot of them have intervals of like 0 to 1 and then 1 to 2, 2 to 3. So it might be a good idea to figure out what the behavior is at each of these whole numbers. And if it's equal to 0 or if it's equal to a different number, that'll give us a lot of information. So starting off when t is equal to 0, then we are going to have 5 sine 2 pi multiplied by 0.5 multiplied by 0. Sine of 0, of course, is going to be equal to 0. And that's neither positive nor negative, it's just 0. So V at t equals 0 is 0. If we have 1 sine, or 5 sine 2 pi times 0.5 times 1 is also going to be equal to 0. Okay, we're seeing a pattern kind of emerge. Let's do one more for 2. 5 sine 2 pi, because 0.5 and the 2 are going to cancel out. That is also going to be equal to 0. All right, this is useful information because it tells us that whatever our graph is, it has to be at 0, at 1, at 2, at all of these whole numbers, it has to be equal to 0. That actually lets us eliminate E and F as choices, because you can see that they're at 1, 2, 3, whatever, the graph isn't equal to 0. But that still leaves us a lot of options in terms of what the other graphs could be, because we don't know the positive or negative behavior. So let's try to determine some of that positive and negative behavior in between these whole numbers. And let's start off with 0.5. For 0.5, 5 sine 2 pi times 0.5 times 0.5. If we calculate that, it's going to be essentially the same as sine of pi over 2, and that is going to be equal to 1. And that means that this value is positive. All right, let's try 1.5 because it's in between 1 and 2. 5 sine 2 pi times 0.5 times 1.5. 1.5, just barely squeeze it in there. That is essentially going to be the same as 1.5 times pi inside of the sine function. And I'm sorry, I forgot to multiply this by 5 over here. So this is actually going to be equal to 5 because it's 5 sine. Anyway, multiplying 1.5 times pi inside of the sine function, and then multiplying that final answer by 5 is going to give us negative 5. And that is going to be a negative number. All right, we now have the information that we need to solve this problem. So a normal sine wave will, of course, look something like this: positive, negative, all that. So we know that we are looking for a sine wave that behaves kind of like this. And we know that at this negative time, when V is negative, that's when our diode is going to be off. So we essentially want our graph to look like this graph up here, except only show the positive values. When the value is negative, we want it to be a straight line that would go right here because it's going to be equal to 0. So we would end up having a graph that looks something like this, where normally there would be the negative sign part there to loop it all together, but since we're neglecting that negative part, we're totally cutting it out. This is what our graph would look like. Looking up here, we can see that the graph that looks the most like that is going to be graph A right here. It shows the exact correct characteristics, so our answer for this problem is going to be A. All right, so question 14 asks, it says an N-channel MOSFET with transconductance K equals 1 milliamp per volt squared exhibits the drain current versus drain voltage relationship shown below. The dashed line, which is right here, the dashed line marks the boundary between the triode and saturation regions. What is the threshold voltage VT of the transistor? So if you've seen a graph like this before, it's going to look something like this. And on this side, we're going to have the triode region, and this side, we're going to have the saturation region. And it's asking us to find the threshold voltage. In order to find that, we're going to have to use this equation right here. The drain voltage is equal to the gate voltage minus the threshold voltage. This is a pretty simple thing to solve because we are given both the drain voltage and the gate voltage based on this graph right here. And we want to find these values. We want to take them based on these points right here that are on the dotted line in between the triode and the saturation region, because that is where the threshold voltage is. The threshold voltage is the voltage that marks in between those two spots. So for when the gate voltage is equal to 5, for example, we know that the drain voltage of this point right here is basically going to be 4 because it's, you can see that on the x-axis of this graph. So if we plug those into the equations with the gate voltage equal to 5 and the drain voltage equal to 4, we will have 4 is equal to 5 minus VT, and that gives us a threshold voltage of 1 volt. And we can try this with all of the other points on this line here. If we have 3 equals 4 minus VT, 2 equals 3 minus VT, 1 equals 2 minus VT, all of these right here are going to give us a threshold voltage equal to 1 volt. And this is always going to be consistent. It's always going to give you the same voltage threshold. So we know that the answer for this problem is going to be 1 volt. Moving on to question 15. This question says, Sources of output signal nonlinear distortion in a common source MOSFET amplifier include, and then it gives us several options, including cutoff clipping, triode flattening, quadratic distortion and saturation, and some combination of these terms. So this question, unfortunately, is going to be basically memorization, but the correct answer is G, and I will explain why. This question is basically memorization, but I will explain each of these terms individually so that you can gain some kind of familiarity with what those concepts are. So if you imagine you have a graph that shows the relationship in between the gate voltage and the drain voltage of a common source MOSFET amplifier, you're going to have a curve that looks something a little bit like this. In between these two dashed lines that I'm going to draw right here, that is going to be the saturation. That's going to be the saturation region in the middle, right there. Then on the left side of this dashed line, that's going to be the cutoff region. And on the right side, that is going to be the triode region. So when we are looking at the saturation region, the way we usually model it is as a linear relationship. But if you look at the actual curve, you can tell pretty obviously that the saturation, it's not actually a linear relationship in between these two terms. So even though we model it as a linear relationship, it's not really. It's usually pretty linear for like this very middle part right here. But on the edges, as you get closer to these cutoff and triode regions, it's going to be less of a linear relationship. So starting with cutoff clipping, that's two P's, sorry. Anyway, cutoff clipping, let's say you have a triangular wave that looks something like this. Cutoff clipping is going to be when you are looking at a point on this saturation curve right here. You're looking at a point that's getting increasingly close to this cutoff point right here. If you're looking at a point that's really close to there, you're going to experience some distortion just based on the fact that you're so close to that cutoff region. And the distortion is going to look something like this when you view it on your waveform. Where the very top of your waveform gets kind of cut off, and that's why they call it cutoff clipping. If you're taking ECE 2K7, you might have seen this in your labs. For certain circuits that you build, you might have seen or experienced cutoff clipping. So triode flattening is the next type. Let's take the exact same triangular wave. This is a very rough sketch of it. Anyways, triode flattening is basically the opposite of cutoff clipping. It is when you're on the saturation curve right here, but you get a little too close to the triode region, and it's a bit of distortion that's introduced from that. And triode flattening looks a bit different than cutoff clipping. Triode flattening occurs in a way that the slope of your waveform is going to be decreased in magnitude. So instead of having, straight lines like this that are, equal to the slope, you're going to have partially a straight line, but then the slope is going to decrease, and the amplitude of your waveform isn't going to be quite as high as it was without the triode flattening. So I made that one too high, but you can see the kind of idea. If you notice in the triangular wave, they kind of come up to about there, but triode flattening, they fall a bit short because the slope has been decreased and thus the amplitude of the output has been decreased. And the very last one we're going to talk about is the quadratic distortion. And this one is basically because of that linear relationship I was talking about earlier. The linear relationship being an approximation, not an exact thing, because obviously the saturation curve isn't exactly linear in the way that we approximate it to be. So quadratic distortion is going to, quadratic distortion is going to get you a wave that doesn't look quite, oh, sorry, this is like the original triangle one. But if your original triangle wave looks like that, quadratic distortion is going to get you a wave that where the lines aren't exactly straight. They're like a little rounded or a little strange looking. It's not exactly a linear relationship. All right, and in a common source MOSFET amplifier, all three of these are going to be present. So the correct answer is G, A, B, and C. You just need to remember, you don't even necessarily need to know what each one of these are. It might just help you in the future, but you just need to remember that all three of them are going to be present in a MOSFET amplifier of this kind. The following two questions pertain to the common source amplifier circuits shown below. The MOSFET threshold voltage is Vt is equal to 0.5 volts, and the transconductance parameter is K is equal to 2 times 10 to the negative third amps per volt squared. All right, this this problem is dealing with a circuit with a small signal linear amplification, which is a different kind of circuit than a normal MOSFET circuit. And one of the big giveaways that we're dealing with this kind of circuit is, first of all, the word amplifier in the problem statement is telling us that we're dealing with amplification. And also this over here, if we look at the voltage source, it has two parts in it, one with the uppercase V and one with the lowercase v. And this uppercase V is going to be like the DC voltage. But this kind of voltage source also has an AC component to it. So when you have these two components, that's going to be like a giveaway that we're using a linear amplification. And that's the kind of circuit that we're doing right here. So some equations for this type of circuit are given up over here, and I would really recommend writing these down. If you want to learn more about why this circuit is different than a normal circuit, I would recommend reading the textbook, because I don't think I can explain that to you in a short enough, condensed enough version for it to be in this video. So if you want to learn more about why this circuit is the way it is, definitely read the textbook. But if you have these equations, you have all you need really to solve this problem. So question number 16 is going to ask us, at what gate voltage does the transistor operation change from saturation mode to triode mode? And for this one, we want to use our first equation up here, because that's going to give us the gate voltage at B. And in this situation, if you remember our little our voltage versus voltage graph, we've got point A here and point B here, and this is the cutoff region, this is the triode region, and this is the saturation region in here. So CST, let's abbreviate it like that. What we're looking for is what the gate voltage would be at this point B here, and that's why this voltage has G and B, because it's the gate voltage at point B. That's why the B is in there. All right, so if we use this equation to try to solve question 16, we can write it like this, equals, we know that VT is equal to 0.5, and then we can put in the square root up here, 2 multiplied by K, which is 2 times 10 to the negative 3, so 3, multiplied by RD, which is equal to 2,000, multiplied by VDD, which is 24 volts. All of that right there is going to be plus 1 inside of the square root, and then we're going to have a minus 1 outside of the square root. And then all of this is over K, which is 2 times 10 to the negative 3, multiplied by RDD, or sorry, just RD. That's a typo that it's got more than one in there. Let's cross that out, just RD. And RD is going to be equal to 2,000. All right, so if you solve this equation, you're going to get VGB is equal to 3.72, and that corresponds to answer D for number 16. Number 17 asks, what is the magnitude of the small gain A of the amplifier for a gate voltage of VG equals 2V? We're going to use the second equation right here. The A in this stands for amplification. So AV equals negative RD K. I guess I don't really have to rewrite this. Anyway, RD is going to be 2,000. K is going to be 2 times 10 to the negative 3. And then we're going to have VG minus VT. VG we are given as 2, and VT is 0.5. And based on that information, we can solve AV, and it will be equal to 6. So the correct answer here is going to be 6. Question 18 says, determine the load voltage VL. Write your answers in the box in the lower right corner. On the real test, the box would be like down there, but I don't have the box shown on this example. All right, so this circuit kind of deals with the idea of transformers, which is this over here. It looks pretty similar to a mutual inductance problem. The only difference is these two lines in the middle make it like a slightly different kind of concept, but they are very similar. So when we're solving this kind of circuit, we have this ratio right here, which is going to be N, and it's going to tell us the ratio between the terms on either side of the transformer. So when you are kind of dealing with something like that, if you have like a current on this side, for example, it's going to be 5 times more than the current over here on this side. And they're always going to be that relation. The voltage drop and the resistance is going to be the same with that relation. The resistance actually has a special rule, but the voltage drop will be similar. And then because we've got this dot and this dot on opposite sides to show that these are kind of polar, they're opposing, that means that we also, when we're converting from one side to the other, we're gonna see that those voltage drops and those currents are going in different directions. They're gonna be going in opposite directions on each side of the transformer. All right, so jumping into how we would actually solve this problem specifically, the first thing that we kind of want to do is to simplify the circuit by kind of taking these two individual sides here and combining them in a way that allows us to solve for the current going through the primary side of the circuit. And the way we can do that is by, we only have one impedance or resistance value on the secondary side of the circuit. So what is easiest for us to do is to kind of move this over and see if we had like an equivalent circuit, a circuit that behaved the same way, but it just had a resistor value right here instead of having this transformer, what would that circuit kind of look like? And the way we can do that, we can just, sorry, this is that. We can just redraw the circuit a little bit. Oops. To look kind of like this, where we have those two resistors. This one, or sorry, 3 resistors, I guess. That one's 2 ohms, this one's 4 ohms, and then this one is going to be the equivalent impedance. And the way we can find that value is by taking this resistance value right here, which is 100, and then multiplying it by n squared. And if we do that, it's going to be kind of the same as multiplying by 1 over 25. And so you would have the value of 100 divided by 25, and that is going to be 4 ohms. So we know that this C equivalent value is actually going to be 4 ohms. Now we want to do some resistor combining, which should be pretty easy for us at this point in our ECE 2K1 learning. We know that the equivalent resistance of these two parallel 4 ohm resistors, it's we're going to use this equation to solve it, and when we do that, we're going to get an equivalent resistance of 2 ohms. So if we redrew this circuit with just one resistor here, it would be 2 ohms. And then when we want to add 2 ohms to the equivalent resistance, which is 2 ohms right there, because they're in parallel, we would get 2 ohms plus 2 ohms, which is equal to 4 ohms. So if we want to completely redraw the circuit, it would look like this. That's a resistor, and it is 4 ohms. And our V value is 10 VRMS over here. Okay, using this and Ohm's law, we can now solve for the current which would be going through here. The current is like going through there. It would be the same current going through there and up here. I'm going to call this I1. From Ohm's law, we know that I is going to be equal to V divided by R, which in this case is going to be 10 divided by 4, and that gives us 2.5 RMS amps. That is the value of this current going through here, but once we reach this node right here, the current is going to split, which is the same node as right here. It's going to split, and because we see that 4 amps and 4 amps, it has identical resistance values, this current is going to split evenly in half because it's going to reach, or it's going to see the same amount of resistance from both of these two sides. So say we kind of want to find the current going through there. I would call this I2. I2 is going to be exactly half of I1. And that is going to give us a value of 1.25 ARMS. All right, so that current right there is going to be the current that's going through this side of the transformer. That's I2 right there. And if we want to find the current coming up this way on the other side of the transformer, we just need to use this ratio value, as well as the fact that these two, it's an opposite. So this current would be going in the opposite direction. It would be going up like this, and let's call that I3. I3 is equal to, it is equal to negative n times I2. which means it's going to be equal to -1/5 times 1.25. And that means our I3 value is going to be equal to -0.25. All right, we're almost done because that is going to give us the current that goes all the way through here, including through where our voltage drop is that we're trying to find. The last thing we have to do is just use Ohm's law one more time to find our final value. V is equal to IR. Let's just call it that. So -0.25 multiplied by 100, which is what we have up here. And that is going to give us a VL is equal to -25 VRMS value. And that is our final answer for question number 18. That is what VL is equal to. Question 19 is a two-part problem that I've split into two separate questions in the exam when you're solving the exam. But so I'm going to go through each part individually. Part A asks, in the ideal diode circuit below, find the value of resistor R1, which gives a diode current of ID is equal to 900 milliamps. So we know that ID, which is right here, ID is going to be 900 milliamps or 0.9 amps, whichever way you want to write it. And then we know for certain that the current going through here is positive. It's going in the same direction as the diode is pointing. Because the diode is pointing this way in the arrow and the current is going through in the same direction, we know that this diode is forward biased. And that means that the voltage drop across the diode is going to be equal to 0, because every time a diode is forward biased, the voltage drop is 0. So we know that VD is equal to 0, and that of course means that here at this node, that is going to be essentially a ground. So the voltage at V0 is also equal to 0 volts because there has been no voltage drop to get to this point so far from the ground, which was on the other side of the diode right here. Next, what we can do, because we ultimately want to solve for this resistor here, we can solve for the current coming in from this resistor and the current coming, since we already know the current coming in from the diode, and that will give us the current across here, and then we can use Ohm's law to solve for the resistor. So in order to find the current going across this lower resistor right here, we've got to know that the voltage drop from here to here is 10 volts. It's exactly the same because this is the ground here and this is at 10 volts. It's going to be 10 volts because 10 minus 0 is, of course, 10, which is pretty easy to know. And we know that it's going to be essentially the same over here. This is going to be negative 10 volts because this value up here is negative 10 volts. All right, so knowing that, we can now use Ohm's law on the bottom to solve for I2, which is going to be going like this. I'm also going to write an I1 right here for later. But in order to solve for I2, we can use Ohm's law. V divided by R is equal to I. And our voltage is going to be 10. And our resistance is going to be 100. The 10 comes from right here, and the 100 comes from right there. When we solve that, we get 0.1 amps, and that is the value of our I1. Now, in order to determine what I2 is, we've got to sum the currents that we have so far, ID, I1, and I2. So I1 is I1 plus I2 plus ID, all of that is equal to 0. That gives us I1 is equal to negative I2 minus ID. And that is going to be negative 0.1 amp minus 0.9 amps. And when you subtract those from each other, you get negative 1 amp for the current, which means that it's not actually going in this direction, it's going to be going in the opposite direction like this. And then in order to find the resistor, we use Ohm's law one more time. We know that V is equal to IR. That means that R would be equal to V divided by I. So R1 is going to be just like that. R1 is equal to negative 10, which we get from right here. Negative 10 divided by the current that we found in our last step, which is negative 1. That's going to be 10. So the resistor, the value of R1 is going to be 10 ohms. There will be a box in the corner that you can write this answer in. I don't have it just in this explanation video, but normally it would be down in the corner, kind of here. You can write it in the box. All right, on to part B of question 19. This one is essentially a very similar circuit to the previous one. We have slightly different voltages here, but the main difference is going to be that we have two diodes in this kind of square parallel to each other configuration over here. And one of these diodes is forward biased in this direction, and then the other one is forward biased in that direction. Part B asks us to find the diode currents ID1 and ID2, and the diode voltages VD1 and VD2. So what's important to note about this diode configuration right here is that if either one of these diodes are forward biased, and then the voltage drop across that diode is going to be equal to 0. Also, if one of these diodes are forward biased, then the other one has to be reversed biased. So if this one was forward biased, this one would not be turned on. So this diode would be on, but this one would be off because it's the only one that can be forward biased. And then vice versa, if this diode is on, then this diode has to be turned off because the current coming into here would be flowing in just one direction. There's no current coming in here, or like this is the ground right here. So the current the power is coming from over here. And it only has one kind of way to get in before it splits and in those two directions. So we know that it has to be going in the same direction in both of the diodes, right? So that essentially means that no matter what, we're only going to be looking at one diode at a time when we're trying to figure out what the diode voltages are. Okay. In addition to that, because as I said earlier, if either of the diode voltages, or if either of the diodes are turned on, the diode voltage across that diode must be equal to 0. These voltages are also equal to each other but opposite in sign. But if one of them is equal to 0, that means that the other one is also equal to 0. So because we know that at least one of them must be equal to 0, and that if one of them is equal to 0, then the other one must also be equal to 0, we can actually say right away that both of these values are equal to 0. And let's write that down in our little answer spot over here that I've picked. Both of those are going to be equal to 0 volts. All right. And then we also know that because the current can only flow through, it can only be flowing in one direction at a time, and both of these diodes are in opposite directions, that means that the current is only going to flow through one branch of these two diodes at once, which means that if the current is going through here, there is no current through here, and if the current is going through the second diode, there's no current in the first diode at all. That means that one of these two currents has to be equal to 0, and the other one has to be equal to not 0 if there's a current present at all. All right, now that we've determined this, we know that 3 out of our 4 answers are actually going to be equal to 0. That makes it easier to solve for our very last diode current. And as of right now, we don't know which diode current it is, whether it's ID1 or ID2, but we know that one of them has a possibility of being non-zero. Yes, and so the way that we find out what the current is going to be going through these diodes, we're going to look at the current coming from this branch, the current coming from this branch, and the current going out into the two diode configuration that we have over there. And we can do this using a simple like current addition at this junction. If we say that across here we've got I2, down here we've got I1, just like in the previous problem, and coming out of here we have ID, then we know that I1 plus I2 is going to be equal to ID because the current is coming out of here. And of course the direction that we picked for ID is completely arbitrary. If you want to say that ID is going in and just have them sum all up to 0, you can do that as well. All right, now using Ohm's law, we can say that V1R1 plus V2R2 is going to be equal to ID. And luckily, we are given all of these values in our problem up here. This is going to be V1, R1, V2, and R2. So we can just plug that back into our equation. Negative 9 over 1,000 plus positive 9 over 100 is equal to ID. And then we're going to find that ID is equal to 0.081 amps. You can also write that as 81 milliamps. All right, that means that we know that the current is going to be flowing in this direction out of the junction right here, and it's going to have a positive value of 81 milliamps. Since it's positive, we know that the current cannot be flowing in this direction because it's going to hit this diode, which is biased in the other direction, and it's not going to allow the current to go through. Which means that all of the current coming out of this junction is going to go down through the second diode right here and out here, and that's the direction that all of the current is going to go. That means that we know that this current has this diode has no current going through it. So the current of diode 1 is going to be equal to 0 amps. And since all of the current has to be going through this diode here because it's the only one that's forward biased, we know that this one is going to be 0.81 amps. And you can also write that as 81 milliamps if you would like. So this is the final answer to number 19, part B. Question number 20 says, the following 3 parts concern the N-type MOSFET used in the circuit below. The MOSFET's threshold voltage is Vt is equal to 0.5 volts, and the transconductance parameter is K is equal to 2 times 10 to the negative 3 amps per voltage squared. Write your answers in the box in the lower right corner. I took out the box, but on the exam, there would be a box down in the corner, probably like over here or something, that you would write your answers in. Okay, what we need to find is the drain current, ID, the drain voltage, VD, and we need to determine whether the transistor is operating in the triode or the saturation mode. So very first thing, we have a series of steps we want to go through whenever we're solving a transistor problem. This problem tells us that this transistor is not in the cutoff mode, but normally what we would do is we would test for the cutoff mode, then we would test for saturation, or we would assume saturation and then try to solve for that. And then the third thing we would do is test for triode mode. This is because these are basically ordered in order of the easiest to solve for to the hardest to solve for. It's very, very easy to determine if a MOSFET is in cutoff mode. It's slightly harder, but still kind of easy to determine if it's in saturation mode. And then it's hardest to determine if it is in triode mode. So we want to start with our easiest, the easiest possibility, and then go down till we get to the hardest one. I'm going to show you how to test for the cutoff mode, even though it tells us in the problem that it's not in the cutoff mode, just because I want you guys to know how to do it. So the way that we can determine what mode this transistor is in is by looking at these fun equations up here. If the values that are on the right side of this table are satisfied, that means that the transistor is in the mode specified on the left side over there. So if it's in cutoff mode, that means that VG would have to be less than VT. We can test for this because both of those values are given to us in the original problem. We know that VG is equal to 2 and that VT is equal to 0.5. Obviously, this inequality is false because 0.5 is not greater than 2, so we know that this is not in the cutoff mode. Okay, that was our first step right there. Second step now is to test to see if it's in the saturation mode. And for saturation mode, we would have to use these equations right here. VG is less than VD plus VT. And we already know this first one is true because if VG is not less than VT, then it has to be greater than. So we already know that first one is true. Now, unfortunately, in this problem, we are not told what VD is. Over here, we have an unknown for VD, so we can't immediately determine whether this is actually in saturation mode. So what we do in this situation is we tend to just assume saturation mode. And then we solve, and we solve for VD based on the assumption that this transistor is in saturation mode. And then at the end, we can go back and plug our values back into this inequality that we have right here to check if we got it right in our assumption or not. So if we are assuming that this circuit is in saturation mode, first thing we want to do is to solve for this current here, because using this current, we will be able to solve for VD. And you can see from this equation over here, there are different equations to solve for the current based on what mode you're in. For saturation mode, the equation is going to be ID is equal to K over 2 VG minus VT squared. And if we plug in the values that were given in the original problem, our equation is going to look like this. And it's going to give us a final value of ID is equal to 2.25 milliamps. Now, if we're correct about this being in saturation mode, then that's going to be our answer for A. But before we say 100% that that's true, let's go on to determine VD. So we can see that if we want to determine VD right here in the circuit, one way that we can do it is by finding the voltage drop across here and then subtracting the voltage drop across here, because that's going to give us our voltage drop of VD. And I can kind of redraw that to make it a little bit more clear. There's a resistor there. If we know the voltage drop across here, voltage drop across here, if we subtract those two values from each other, we're just going to know the voltage drop across this region right here. So putting that into equation form, we're going to have VD is equal to VDD, which is the value of the voltage up here, minus, by Ohm's law, RD times ID, which is going to be the voltage drop across this right here, because we know both the resistance of that resistor and the current going through it because we solved it in the previous step right here. So plugging in values, we're going to get 10 minus 1000 ohms times 0.025 because it's in milliamps. And if we solve that out, we're going to get VD is equal to 7.75 volts. And this is going to be our answer for B if we are correct about this being in the saturation region. Now, now we have a value for VD. We're actually able to go back to this inequality that we have up here and plug everything back in to see if this inequality is correct. So VG is equal to 2 2 must be less than 7.75, which we determined right here is the value of VD, plus 0.5. This becomes 2 is less than 8.25. And we can see that this is correct. So we were correct in our assumption in assuming that this was in the saturation region, which is excellent. We can say that our mode is saturation. That is the correct answer for C. And we know that these two answers for VD and ID are going to be the correct answer for this problem. All right, at the end of this video, I just wanted to take a moment and show you all of the equations that I used throughout the making of this video and throughout explaining all of these exam problems. I would recommend that every single one of these equations is on your equation sheet if you're allowed that in the test. So feel free to pause and take a moment to write all of this stuff down. And beyond that, good luck on your exam.